This is section 5.1, using trigonometric identities. So this chapter, chapter 5, our last chapter of the year, covers something that is often referred to as analytical trigonometry. And that means that what you're doing is you're not so much sketching real-life triangles, you're analyzing the properties of these triangles by using the identities. For some people, this is very enjoyable. For others, it's less enjoyable. But in any case, it is good for developing your analytical skills, and it's also, of course, fundamental for calculus. It's fundamental for preparing yourself to take calculus next year. Even odd identities. Now, we've talked about these before. And, when we were doing these in Chapter 4, doing the various trigonometric functions and graphs, we saw which ones were even and which ones were odd. So this is kind of just a review of that. You definitely want to have these written down in your identity chart. You probably have that by now from a previous chapter. But just make sure that these even odd identities are part of it. So sine negative theta equals negative sine theta. Cosecant negative theta equals negative cosecant theta. Cosine negative theta equals cosine theta, secant negative theta equals secant theta, tangent negative theta equals negative tangent theta, and cotangent negative theta equals negative cotangent theta. The easy thing to remember about even odd identities, and I think this is probably going to be helpful for you, is that they're all odd except cosine and secant. Secant really just depends on cosine because it's simply 1 over the cosine. So you really don't have to remember that much. They're all odd except for cosine and secant. Cosine and secant are even, whereas everything else is odd. Now, even and odd is really just based on the symmetry of the graphs. And if you look at the parent cosine function, you can see that it's symmetric about the y-axis. The same is true of the secant. And if you look at the parent sine, cosecant, cotangent, and tangent graphs, you can see that they're symmetric about the origin. That's really all that even and odd comes down to. But when we express even and odd algebraically, these 6 equations are how we express them algebraically. The fundamental trigonometric identities, besides the even-odd identities, are on this screen. Again, you should already have these written down somewhere. But what we do in this chapter is going to reinforce your knowledge, and getting practice using the trigonometric identities will help you to learn them. So just make sure that everything on this screen and on the last screen is in one place in your notes, and you can call it your identity chart or your identity page. Let's look at some examples. And as we're doing these examples, the main thing that you're trying to do, all right, your main strategy, is to manipulate functions using the identities. And you'll see what I mean. Let's say that you want to simplify sine x cosine squared x minus sine x. Well, the first reaction when you see that is it looks like an ugly expression, right? Sine x cosine squared x minus sine x. But if you simply use the identities and some basic algebra, then you'll see that it's possible to simplify this expression. What I'd like you to do, just to challenge yourself, is pause the video, see where you can go with this, and then resume when you can't proceed any further. So the first step is to factor out the sine x. You probably thought of that. And so we have sine x times cosine squared x minus 1. Now, the next step is to use a trigonometric identity. And as you can see, we're using one of the Pythagorean trigonometric identities, which states that sine squared plus cosine squared equals 1. We can see that if we manipulate that expression, we would be able to solve for sine squared and get 1 minus cosine squared. And then taking the negative of that would just give us negative sine squared. And so therefore cosine squared x minus 1 simply becomes negative sine squared x because of the Pythagorean trigonometric identity, which says that sine squared plus cosine squared equals 1. And finally, we have negative sine cubed x. As you can see, that's much simpler than the original expression. Factor secant squared theta minus 1. Pause the video, try to do this, and then resume when you have your answer. Now you should have recognized that this is just a difference of squares, and so we have secant theta plus 1 times secant theta minus 1, and that is the factored form. How about factor 4 tan squared x plus tan x minus 3? Pause the video, try to factor that, and then resume. You get 4 tan x minus 3 times tan x plus 1, and if we try to do the FOIL method on this, we can see that it's true. First outside, inside last. So doing the first, we have 4 tan x times tan x. That gives us 4 tan squared x. Doing the outside, we have 1 times 4 tan x. Doing the inside, we have minus 3 tan x. And of course, 4 tan x minus 3 tan x is just tan x. And finally, the last terms, minus 3, or negative 3 times positive 1 gives us negative 3. And that's why we end up with minus 3 at the end. How about factoring cosecant squared x minus cotangent x minus 3? Now before you pause the video, I need to give you a little bit of a hint on this one, and this is a hint that you can keep in mind if you ever see something like this. When two different trig functions are present, put one in terms of the other, then proceed. And then you can factor. The reason this looks complicated and difficult is because cosecant is different from cotangent, but just put one in terms of the other using an identity. Pause the video, try to do that on your own, and then resume when you have a factored expression. First thing to do is to replace the cosecant squared x with 1 plus cotangent squared x. And that, of course, comes from one of those Pythagorean trig identities, which states that 1 plus cotangent squared x equals cosecant squared x. So we replace that. I put it in blue just to show that it's the same as cosecant squared x. And then we can combine like terms, and we end up with cotangent squared x minus 2. And that is easily factorable into cotangent x minus 2 times cotangent x plus 1. Let's look at another example. Simplify sine t plus cotangent t times cosine t. Now we look at sine t plus cotangent t times cosine t, and it looks really complicated because we have now three different trigonometric functions. And so let me give you another hint for this one. When more than two different trig functions are present, put all in terms of sine and cosine, then proceed. You can usually put them in terms of sine and cosine. As you know, the tangent really relates to sine and cosine, because tangent theta is just sine theta over cosine theta, and cotangent theta is just cosine theta over sine theta. And so you can always put things in terms of sine and cosine. So sine t plus cosine t over sine t times cosine t is our first step. And all we did there is we replaced cotangent t with cosine t over sine t. Now at this point it's really just using algebra, so this is good practice for you. You should pause the video and don't resume until you've simplified as much as you can. Alright, we have sine t plus cosine squared t over sine t. Next thing we want to do is get a common denominator. So we multiply sine t by 1, and I'm calling it 1 because anything over itself is just 1. So we multiply by sine t over sine t, and then we end up with sine squared t plus cosine squared t over sine t. And finally we use another Pythagorean trig identity, which states that sine squared t plus cosine squared t equals 1, and so we have 1 over sine t. And that, of course, is the same as cosecant t. So our final answer is cosecant t. That's as simple as we can make this original expression. One last example. Simplify sine x over 1 plus cosine x over sine x. Alright, now the temptation that some students have is to look at cosine x over sine x and think to themselves, oh, that's cotangent x. But don't fall into that trap because that's really not going to help you. Where you want to go with this is putting the expression into one with a common denominator. All right, so with that strategy in mind, pause the video, try to simplify this as much as possible, and then resume when you can simplify no further. All right, so the first thing you want to do is get a common denominator. We multiply the first term by sine x over sine x, and we multiply the second term by 1 plus cosine x over 1 plus cosine x. And what that's going to give us is sine squared x plus cosine squared x all over the common denominator of sine x times 1 plus cosine x. All right, now you should recognize that sine squared x plus cosine squared x is present in the numerator, and therefore we can simplify that using a Pythagorean trig identity, which states that sine squared x plus cosine squared x equals 1, and so we have 1 plus cosine x over sine x times 1 plus cosine x. So we are making some progress. Now the next step you can see is to cancel. We can cancel that 1 plus cosine x in the numerator with the 1 plus cosine x in the denominator, and we end up with 1 over sine x. And that, of course, is the same as cosecant x. Now, I realize that cosecant t was the example for, or was the answer for the last example. Cosecant x is the answer for this example. Of course, the answer is not always going to be cosecant, but the point in both this example and the previous one is that you can often simplify expressions significantly just by using basic algebra and the trig identities. Classwork, page 379, write these numbers down, and see you in class.